All right. All right. Hi, everyone. Thanks for coming. Maybe before we start with the seminar, do we have any announcement? General announcement? No? All right. Okay. Well, so our speaker this week is Miquel Colom Bernadich. He's originally from Barcelona. He did his undergrad at the University of Barcelona, then went to Sweden and also Germany for his master to work on ULXs and eROSITA data, pairing eROSITA data, and is now a senior PhD student at Bond, working with MeerKAT and all the cool pulsar surveying and timing that they've been doing with MeerKAT, precursor of SCIAs. So talk to us about this PhD work. Thank you.
Thank you. You call me a senior PhD student, but I still feel like it's the first year where I... No. But I guess we all feel this way at some point. So, yes, thank you for having me here. So, well, what I will talk about here today is on the pulsar of science that we have been doing with the MeerKAT radio telescope, in several projects that are happening at my institute, and also, of course, with details on my involvement in them. Is this not?
Not that one. One.
This one. Okay.
If you, that side's one.
There we go. So my work is based on studying pulsars, and I think that most of you already know what a pulsar is, but just in case, a pulsar is kind of like a lighthouse in the universe, right? So in a lighthouse, you see a lighthouse at night. It's an object that emits a beam of light, and as this beam rotates, we see it as a single pulsars. Like when a ship that looks at a lighthouse will see the signal as pulsars. And a pulsar works the same way. It's a neutron star that emits two beams of radiation, and as it rotates and the beams sweep the Earth, we see them as pulsars in our radio telescopes. The origin of these pulsars are, of course, neutron stars, which are the collapse cores of former massive stars that underwent supernova. These are very compact objects with a diameter shorter than 20 kilometers. They are highly magnetized, and they can have very fast spin periods. So I know that many people here are working on neutron stars, and one of the magnetars in particular as well. But one of them of observing neutron stars and magnetars as pulsars is to find a timing model where you, for example, measure the spin evolution of these objects, right? And for that, what we do is we observe these objects from Earth, and we measure the times of arrival. And from the measurements of times of arrival, we make this model that describes and predicts every single rotation of the pulsar. However, this is not a straightforward task because in the first place, the telescope on Earth is moving along with the planet, which means that we have to make several corrections. And the first correction that we make is that we move the measurement of the time of arrival of the pulse from the reference frame of the Earth to the reference frame of the Sun, which is the barycentric solar system barycenter. And to do this, we apply all of these corrections to the times of arrival measured on the Earth. And these include the Romer delay from the changing position of the Earth around the Sun. This includes also the Einstein delay, which is the correction of the relativistic time dilation because the Earth has changing velocities across its orbit. And also the fact that the Sun is a gravitational lens that affects the propagation of the signal through the solar system. But my work in particular focuses on what happens if the pulsar is found on a binary system, where you also have to apply all of these corrections, but on the other way around, on the frame of reference of the pulsar binary. And this allows you to measure very interesting things. For example, you can describe the Keplerian parameters of the orbit, and you can measure how they evolve with time. And one of the measurements that we can make, for example, is the advance of periastron of the orbit, which is analogous to the rotation of the orbit of Mercury because of general relativity. We can measure how does the companion of the pulsar and its gravitational field affect the propagation of the pulsars. And we can also measure the instant delay, which I mentioned before, which also measures the change in the rate of passage of time in the frame of the pulsar as it moves in an eccentric orbit around its companion. And we can use those to measure masses in the binary. This method was used, for example, in 1972 to measure the orbital decay of the first pulsar in a binary system that was discovered. And in here, what I plot is the cumulative advance of the passage of periastron. This means that the orbit gets shorter over time. And this warranted a Nobel Prize in 1993 for the first indirect detection of gravitational wave emission, which had been predicted earlier in the century. We can also use this to measure masses and constrain the physics of condensed matter. For example, in this plot here, possible equations of states in mass and radius are shown for neutron stars, which are derived from theoretical models. And measuring the masses of very massive neutron stars allows us to see which of these models are good or are consistent with the measured masses and which are not consistent. One very recent study that I think is the best example of the power of the pulsar timing technique is the recent studies published in 2021 on the double pulsar, which is a system where the two objects are actually pulsars that are seen from telescopes. Even though pulsar B precessed out of view in 2006, it is predicted that it will come back in a few decades. In here, which I show once again the shortening of the orbital period with time, and I should indicate that the red line is not a fit, it's the prediction, and the blue dots are just the measurement plotted on top of the prediction. So this system proves general relativity to high precision. And I can also show here the measurement of the Shapiro delay. So this system is also we are very lucky in this system because this, the orbital plane is only separated, is only inclinated by 0.7 degrees, which means that this system is extremely edge-on, and the pulses of the pulse array go as close to 11,000 kilometers from pulsar B. And this creates delay because the light rays have to overcome a larger distance as they travel through the gravitational field of B. And this creates this very characteristic delay with pulsars getting delayed as conjunction approaches. And this experiment consists of a test of gravity with light in the largest space-time curvature that has ever been made. And in here I compare it with other experiments, the famous images made by the EHT that have images the photon rings of black holes actually prove a space-time curvature that is smaller than what is given by this test. And also, of course, it's much better than the classical test that was made on this phenomenon with the Cassini probe. Using these measurements, given that each relativistic correction to these signals, which cause these signals that we measure, depend on the orbital components of the orbital parameters of the orbit and the masses of the components, this allows us to constrain which are the possible masses in the system. And in this case, we see that all of these measurements converge in a single point in the mass of the pulsar and the mass of the companion, giving us what is the most precisely measured neutron star masses that we have right now. And another effect that has been only measured in this system and nowhere else so far is the fact that the Shapiro delay is so precise in this system that not only we measure the time delay of the pulses as they travel close to the companion, but we also see their deflection. So if this pulsar is rotating clockwise, we see that before conjunction occurs, the light rays bend slightly to the left, which means that the pulses will be detected with a slight delay, and as we go past conjunction, the opposite occurs. Right now, the pulses bend slightly to the right, and then they arrive at an earlier time. And this is the only place where this phenomenon, the only experiment where this phenomenon has been measured. So now I have convinced you of the usefulness of doing pulsar timing. So I will start with the pulsar science that we have been working on with the MeerKAT radio telescope. So first of all, I will introduce what the MeerKAT telescope is. It is a radio telescope operated by the South African Radioastronomie Observatory, abbreviated as SAREO, in the Karoo Desert in South Africa, right here. And it is, of course, an interferometer. Right now, it contains 64 antennas, each one of them 13.5 meters in diameter, which have a collecting area of over 9,000 meters square. Now, in here, you can see a map of the antenna array on the desert. What is a novelty with this telescope is that, aside from being an interferometer, it also has a much larger collecting area than the previous most powerful telescope in the Southern Hemisphere, which is the Parkes telescope in Australia. And of course, we can also compare it with other telescopes on the Northern Hemisphere. The one that I have been working with also in Germany is the Effelsberg telescope, very close to Bonn. And of course, it doesn't compare in collecting area to the former Arecibo telescope and the FAST telescope in China, but these telescopes are not seeing the same sky, so they are very complementary. And right now, there are 3 available receivers on the MeerKAT telescope. One, the UHF at low frequencies, the other one at L-band, which is around the 21 centimeter wavelength, and then the higher frequencies at S-band. And we will see later how having these different receivers is actually very useful. So now I will explain explain the work that we do with MeerKAT as a pulsar search instrument, searching for new pulsars. And first, I will talk about how does MeerKAT see the sky. So this is the size of the beam of a single antenna on the sky, and it has a diameter of 30 arc minutes. This means that using the diffraction law, this has been calculated using the diffraction law at a particular wavelength, 21 centimeter in particular. This means that if you have a pulsar at the center of this beam, you will observe it with a maximal signal to noise. And as you move away from the pulsar, the signal to noise will reduce until you reach the half-width maximum. And then outside of the beam, you will lose the signal. This is much larger than the former most powerful telescope in the Southern Hemisphere, because the antenna size is much smaller. Therefore, the diffraction pattern becomes larger, right? But the advantage is that MeerKAT is an interferometer. And by doing interferometry, you can coherently record the signals of different antennas to create a beam that is much smaller. We're reaching the resolution of arc seconds, which is much better than any other telescope that we have so far, any other radio telescope that we have on ground working at the 21 centimeter wavelength range. The advantage of this is that since this small beam is created by software through computation, it means that you can create many of them, and you can fill the area that is seen by the single antenna, you can fill it with many beams in a single observation. And this is a technique that many of these projects that have been using, right? So this is TRAPUM, which is transients and pulsar searches with MeerKAT. And there are several projects that have been working with this telescope. And so far, we have 184 new discoveries out of the population of 3,000 pulsars that we know in total. Some of these are, for example, the surveys in the nearby galaxies, which have discovered 7 new pulsars in the Small Magellanic Cloud and 7 new pulsars in the Large Magellanic Cloud, and they have searched also for pulsars in other nearby galaxies without success so far. But they all have already duplicated the amount of pulsars that we knew in the Small Magellanic Cloud, for example. Another survey is the Fermi sources survey, in which they have selected 79 Fermi sources from the Fermi catalog that have pulsar-like characteristics in their emission, but pulsations have not been detected in the gamma ray. So they followed them up with radio and with MeerKAT, and they discovered 18 MSPs. And many of those, after the radio ephemeris had been found, now that we have an orbital ephemeris, the gamma photons have been folded with these ephemeris, and gamma ray pulsars have been found, have been uncovered, that which were previously unknown. Another very huge project is the search of pulsars in globular clusters. And as you can see, many discoveries have been made since 2019, which is when the MeerKAT telescope had first light. But the projects I want to focus on is on the MeerKAT Max-Planck-Institut for Radioastronomy galactic plane surveys at L-band and S-band, which is where I have been the most involved. So these are two surveys that happen at the frequency of 128 GHz and 2.4 GHz. And as you can see on this map, are focused on the galactic plane. The reason why we focus on the galactic plane is because where binaries tend to stay. So pulsars are born with a supernova kick, and isolated pulsars tend to have a more spread distribution on the sky. But since binaries are heavier, the kick doesn't give such a velocity in total to the binary, and they tend to stay on the galactic plane. And in particular, we observe the region that is not observed by other powerful telescopes in the Northern Hemisphere. And these areas of the survey area are covered in a tiling pattern, which ensures proper coverage of the sky using single pointings with the beam, and each pointing we produce 480 Coirin beams, and this covers with an overlap that seeks to leave as little holes as possible in the sky. So very quickly, how do we do a pulsar search? In this data, there is a pulsar. We just don't see it right now. Here we see the frequency at which we observe light, and here we see the time series, because this is a time series for each frequency channel. The problem is that radio emission is highly dispersed. So there's this dispersion measure. 3 electrons tend to delay the arrival of light at lower frequencies. So what we have to do is correct for this delay until we recover a pulsar signal in the data, and then we can fold it and see the signal. Problem, for a pulsar that we don't know the dispersion measure, so we don't know which dispersion measure to correct with. And pulsars are also extremely faint. It's very uncommon that we see the pulsars. So we have to use, to find periodicity, we also have to use other algorithms that identify a signal, such as the fast Fourier transform or the fast folding algorithm. So in the end, we do a loop where for each beam, we do a dispersion measure trial, and then we search for candidates, and the search for candidates is repeated at each dispersion measure trial, and then we inspect the candidate. But we have another problem. We want to look for binaries, and fast pulsars don't want to be found. So in here, I show a pulsar moving on a binary, and as the pulsar moves away from the binary, the Doppler effect tends to enlarge the time between pulses. Well, when it's coming towards us, the opposite happens, right? So different parts of the orbit, the pulsar will have a different spin period. And this can be shown in this plot here, where we see that the observed period changes over time for a mock pulsar with this spin parameter, this orbital period, and this orbit and this size in orbit. The big problem is that our observations are not instant. They span a certain amount of time, and if your observations happen at the point where the pulsar is changing its spin period, then you lose the periodicity in the signal. It's not a periodic signal anymore. The period shifts through the observation. And this is a classic plot from the 90s where this was first discussed, where they simulate observations which are 1,000 seconds long, which is around 20 minutes. And they simulate a binary with 0.3 companion and a regular pulsar. And they say, how much is the noise, the signal to noise, how much of the signal to noise is lost because the pulsar is in a binary. And they see that for short rotation periods and short orbital periods, the signal to noise is very quickly. This is the ratio of the signal to noise if the pulsar was not in a binary with respect of the pulsar having acceleration because of being a binary. So the compact pulsars and short binaries, which are the most interesting ones, are lost. So to correct for this, we do a time correction. In here, I show a signal of a pulsar in rotational phase, and you can see that in every time that we integrate the signal in spin phase, the pulse arrives earlier, and then it turns around and then arrives later. This is because the pulsar is being accelerated and the period is changing. The spin period is changing through the observation. We can resample this and recover the signal, assuming a constant acceleration, which means that our search actually has a nested loop within the DM loop, where inside of every dispersion measures the dispersion step, we assume an acceleration step, we resample the time series, and then we look for periodic signals. We do this for each one of the 480 beams that we have in each pointing, which are 10 minutes long, and we do 20 pointings per observation, and we do per session, and we do 2 sessions per week, which means that we used to get at LBAN, and we still get at SBAN, a rate of 350 terabytes per week, which cannot be stored anywhere. What we do is we process it on a dedicated cluster in South Africa. In real time, we inspect the candidates, the data is deleted, the next data comes in. And this was successful. We discovered 78 new pulsars, 17 of which are in binaries which have gotten exhaustive follow-up, and for all of them, we already have orbital solutions. And one of the huge advantages of using MeerKAT is that since we have this coherent beam tiling, we can actually detect the pulsar in several beams. We have the best signal to noise detection at the best beam, but neighboring beams can also detect this pulsar, right? With different signal to noise. And we can triangulate this to get an instant position of the pulsar to the arc-second resolution, which is much, much higher than what any other telescope can do at the discovery. For binaries, once we have a discovery, we reobserve it. Well, for binaries and for isolated. But if the pulsar is in a binary, we'll see that in your second observation, the spin period is not the same as in the first observation. That happens because the pulsar is slightly slower, and if you follow the same period every time, the pulsars will arrive at a slightly delayed spin phase, right? So you can use this to measure the period at each observation epoch. And this is what we use to solve a binary in the first place. In here, I show an example from one of our first binary discoveries. And we first ran into a problem. If the orbital period is lower than the observing cadence, the evolution of the spin comes in random. You don't see a nice modulation by the orbit unless it's a few days long. Usually what is done in this case is to use a Lom's-Kargel periodogram to find a periodicity in irregularly, non-evenly sampled data. But if your orbit is eccentric, your signal will not be a sinusoid anymore, and then the Lom's-Kargel is not sensitive to this. So we instead implemented another solving technique, which is basically a fast folding algorithm, but for the observed spin period. So I teach assume orbital period, we fold the data, and then we make an estimate of the roughness of this fold. And in here I show how at a particular, this is the inverse of roughness, so this plot will show the smoothness. So in folds around this area, the resulting fold will result in a random random distributions, and this will not be a very smooth fold. But if you fold at the orbital period, then you get a smooth curve. And this shows up as this peak. And this is the smooth curve, where you see that the points are ordered in the right orbital period. And in this case, we see the eccentricity because the curve is not symmetric on either side. And then you can find the rest of the orbital parameters by fitting with an orbital fit software. But now once we have this, we want to look for a timing solution. And a timing solution is not the same as an orbital solution, because an orbital solution is based on the measurement of the Doppler effect. but it doesn't trace every rotation of the pulsar. This is because while we have been measuring the observed spin period at different epochs, these are observations that are a few minutes long, spaced maybe by a few hours and a few days. And in between each observation, we don't know how the pulse is evolving. And here I show that the pulse can wrap around the phase 4 times, but in practice, we can have 20 phase wraps, 25 phase wraps. It can change direction and go back, right? So a timing solution is able to track this. And to find a timing solution, we instead move into integrating this into high signal to noise pulses, and we measure the times of arrival to the precision of microseconds with MeerKAT. And then using these times of arrivals, we look for a model that predicts them. And there will be only one solution that tracks every single phase rotation of the pulsar. Problem, we don't know how many phase rotations are there in between each observation. So each gap introduces a dimension where you have to find how many phase rotations there are, and each gap and each space between observations is an extra dimension on top of the orbital period. One big help that we have, though, is that since we have a very good localization from the star, this is a parameter that we can already assume as known. And this helps a lot because we can get timing solutions with a data span that is shorter than 1 year, because usually you will have to wait 1 year to be able to measure the position with timing. But since we already have this, we can go ahead much more quickly. We use the Dracula algorithm to find this solution, and the Dracula algorithm will need a whole other talk to explain how it works. But basically, it is an algorithm that is designed to explore the chi-square map of solutions in this phase wrap space in a smart way, exploring different branches and starting with observations that have smaller gaps in between them. And in particular, what I did was to implement this algorithm as a Python router in Tempo 2, so that we could use Tempo 2 to solve these pulsars. And these are the results. In here, I show the orbital period against the semi-major axis of our discoveries, which are marked as stars, and against the other non-binaries that exist in the galactic field and also in the spin period. I will highlight, and also, of course, the farther they are down to the lower right, the more massive are these systems with higher companion masses derived from the mass function. I will highlight a few interesting discoveries that we have. We have these two here, which are these two pulsars. The interesting thing about them is that they're very fast rotator millisecond pulsars with somewhat heavier companions than what we expect for this kind of spin period. This is because they're an arising class of binary pulsars where the progenitor of the companion is a massive star that it happens to be close by to the pulsar originally, creating a very recycled pulsar with a heavier carbon-oxygen white dwarf instead of a lighter helium white dwarf that we see from this kind of evolution. We also have this pulsar here, which at first glance is just a millisecond pulsar with a very wide orbit, but it's coincident with a Fermi source, and we already have detected it. From the radio ephemeris, we have folded some members of our group, along with Colin Clark, have folded the gamma ray data, and they have recovered the Fermi pulsar, the gamma ray pulsar. We also have this one here, which has a circular orbit and is mildly recycled, but its companion is very heavy. And given the circularity of its orbit, the companion is likely to be a white dwarf, and this white dwarf is going to be amongst the most massive ones that we know of already. And of course, we have one of our double neutron star systems that we have discovered, in which I have focused much of my work. This is the plot I have been showing before. And in this case, we already have a full timing solution, which was published this Wednesday. And as you can see, we found we have a good model that describes the arrival of the pulses from the Gaussian distribution of errors in the timing residuals. And we measure several post-Keplerian parameters in this system. The first one being the periastronaut bands, which is measured to very high precision. And we also have low significance detection of the instant delay and of the parameters that describe the Saphir delay. These detections are quite low, but the advantage of them is that they constrain the parameter space on opposite sides. So they still very useful for constraining the inclination angle of the system. This is the constraints. And being the periangstrom bands the most significant one, we get a very precise total mass for the system of 2.6 solar masses, consistent with it being composed of 2 different neutron stars. And in this black contour, I show the constraints that we get if we assume general relativity and force all of these parameters to be consistent with each other. Then this pulsar can only exist in this parameter, in this area, and in this area an inclination angle, giving us an inclination of 57 degrees as well. Very important thing about, very interesting fact about this pulsar is that it will merge in a time that is shorter than the age of the universe. So this is, therefore this joins the family of double neutron star systems that merge within the age of the universe, meaning that they are progenitors of the neutron star mergers seen by LIGO. And we can actually use this knowledge of these pulsars, and knowing the sensitivity of other telescopes, we estimate how many of those we don't see, to estimate what is the galactic contribution to estimate what is the contribution of these systems and predict galactic neutron star merger rate. And we do so because we know the sensitivity of the previous surveys that have been done before. And in this, using this pulsar and the MMGPS survey, we update this value. And here I show that one of the biggest novelties we include is the inclusion of the MMGPS survey at RelBin, which is the most sensitive survey on this part of the sky. These result from each pulsar, we make an estimation of how much do they contribute to the merger rate, and we see that this pulsar in particular is the one that has the smallest contribution, which is understandable because it has a longer merger time than others. But we can update the total expected neutron star merger rate in the Milky Way, and what we show is that while consistent with previous estimates, these tend to go down. So what we're seeing here in this plot is that earlier, when we were discovering the double neutron star system, these rates estimates were increasing because each new discovery say that there were more systems in this galaxy that could create a neutron star merger, right? But as time goes by, despite us having more discoveries, the increasingly sensitive nature of the surveys is actually reducing these estimates because we're scraping the sky deeper and deeper, and we're scraping the sky faster than we're finding new systems. So this is converging into a value for the neutron star merger rate in the Milky Way. Should say we can escalate this value to a cosmic merger rate. And using this, we actually predict that LIGO and Virgo during the OFO run will observe 10 + 8 - 4 neutron star merger rates. This run has been going on for a few months already, and so far they have detected no neutron star merger rate as far as they have told us. So we'll have to see how this comes out in the end. But at least this rate is consistent with previous LIGO estimates. The derived cosmic merger rate is consistent. I should also mention other discoveries which are not binaries that I know that will be interesting for some people here who work on emission properties of pulsar. This is one interesting pulsar that it's a slow one. It has 2 seconds of spin period, but it's a nuller. You can see it nulling. It's shiny. It shines in some parts of the observation. It's turned off sometimes, and this is a persistent behavior. We observe these minor long intervals in every follow-up we have made. This one is another slow one. This is our lowest discovery, and it seems to be something that works a lot and has wildly changing signal to noise on the pulsars. And in fact, it was also detected in the MeerKAT pipeline, which runs on the same data and looks for single pulsars. We also have this one, which is our the discovery with the highest DM. It's very faint and it's highly scattered, of course, at RelBin. And I should mention the early results from the S-band survey, which has already started a few months ago. The S-band survey, since it explores higher frequencies are less affected by the dispersion measure. Therefore, it's aiming to look deeper into the galactic plane. And that's why this is made in this very narrow strip here. And we have 3 discoveries. One of them here, high DM, larger than 700, highly scattered for being at 2400 megahertz. We also have found this one, which is at very high DM as well, and another one at high DM. Not surprisingly, all of these discoveries are at high dispersion measure. You can see these periods, the spin and dispersion measure parameters here. And this is the team who is working on MMGPS. All of this work has been done by all of the members who are shown here. And yes, so everybody has played a part in it. I should also talk, we can leave searching behind, and I will talk about MeerKAT as a pulsar timing facility, because besides search projects, there are also many monitoring projects. And I come back to the measurement that I explained at the very beginning of my talk, where you see this residual that has only been observed in the double pulsar. This measurement was made with 16 years of data from 6 telescopes combined, including Greenbank, Parkes, and Nancy in France. MeerKAT observed this for 3 years and saw the same signal with higher precision. So MeerKAT is a great facility for pulsar timing. And as such, this opens up many experiments that weren't possible before because we didn't have the sensitivity for them in many systems. And a special program has been put forward to make use of this capability. And this is the MeerTime program, which explores fundamental physics with MeerKAT. The MeerTime program has an array of projects inside of them. One of them is the pulsar timing arrays. The recent pulsar timing arrays that have been published do not contain MeerKAT data because it wasn't recorded in time to be analyzed and included, but the International Pulsar Timing Array publication will include MeerKAT data. There's the relativistic and binary program, which seeks to time compact binaries. There's the timing in globular clusters program that uses the new interferometric capabilities of MeerKAT to make new studies in globular cluster, and this actually is a joint project with the TRAPUM, with the globular cluster side of TRAPUM. There's also a 1000 pulsar timing array, which is investigating the emission properties and polarimetry properties for hundreds of pulsars using the sensitivity of MeerKAT. My involvement in particular focuses with the relativistic and binary side, the RelBin. And the RelBin is a monitoring survey of 25 different pulsars, and each one of them could also warrant its own presentation, so there is no way I can do justice to the whole project in the 5 minutes that we have left. The objective of this is measuring relativistic corrections to the orbits and masses in the systems, which in systems where this was previously not possible due to the timing precision of the instruments that we had available. And of course, we combine this data with earlier observations. And I will put as an example J12276208, which is the pulsar I have been working on, which was discovered as early in 2012, but it was discovered 3 times actually, completely independently. And this is a mildly recycled pulsar, 34 milliseconds. It's a millisecond pulsar at a high DM. But if you plot the mass function of this pulsar, you see that at an assumed inclination of 90 degrees, which is the maximum inclination, you get a minimum companion mass of 1.3 solar masses. So, and the fact that its binary eccentricity is very low suggests that this could be a very massive white dwarf as well. The problem is that at the time, the timing baseline and the timing sensitivity didn't allow the detection of post-Keplerian parameters such as the periastronaut bands or the Shafir delay. Therefore, it was targeted to be observed with MeerKAT. And here we have the whole observation, which we add. This is the timing baseline that we have right now, where we have included the previous Parkes multibeam data with the new MeerKAT data at L-band highlighted here in red, and the MeerKAT data at S-band highlighted down here in blue. You can barely see it, but I promise it's in there. And the green data is the new receiver at Parkes, which is the ultra wide low frequency receiver. And here I show the precision of times of arrival from the MeerKAT receivers against the Parkes receivers, and you can see how much we have improved in timing resolution. While before having times of arrival around 20 or 30 microseconds was what we got for this system, now we have many times of arrival below the 10 microsecond precision. But this system comes with challenge. At such high DM, we do suffer from dispersion measure noise, which means that dispersion measure is not constant, it changes over time. And in here I show for the MeerKAT L-band data. In red, we show the low frequency, the times of arrival derived from data at low frequency, and in green, we show the times of arrival derived from data at higher frequency. We can see this evolution here. As it goes up, the low frequency residuals also go up, and as it goes down, the low frequency residuals also go down, which means that we are affected by dispersion measure noise. Problem is that the Parkes multibeam data has very low frequency resolution, so this gets confused with speed noise as well, and this affects the uncertainties that we get in the measurements. Solutions that we have come up with is that we observe this with the ultra-wide low frequency receiver from Parkes that observes this pulsar at a huge frequency range. So we can monitor the frequency variations and put this along MeerKAT observations. We have also used the newly installed S-band receiver on MeerKAT, observing at the 2400 megahertz, going at high frequencies to try to avoid these dispersion measure effects and reduce the noise that we have. And here I compare at the bottom the observations from MeerKAT at L-band and the observations, MeerKAT observations at S-band. You can see how the profile changes significantly, and we don't suffer scattering either at frequencies. And here I showcase the pulse profile plot, the pulse profile, which is also quite different. And we have also planned dense orbital campaigns, both with Parkes UWL receiver and MeerKAT, and here I'm hinting at a Shafir delay measurement, which I will come to very soon. And we model the dispersion measure variations and the spin noise variations with Bayesian modeling using the TempoNest software, which it is a multi-nested. It does a multi-nested sampling of solutions in Tempo to see which is the best DM noise model. And the dispersion measure noise and the spin noise are modeled as if a polynomial. It's a time series that is put on top of the timing solution. Here I show a very constraining solution that we have with a very constraining dispersion measure model and spin noise model. This amount of coefficients mean that we go to very high frequencies where we model this noise. And well, I also plot the constraints that come from the peri-astronaut bands and the constraint that come from the measurement of Shafir delay, and the constraint that comes if we force this to be consistent with general relativity, and we get a very high companion mass of 1.4 solar masses and an inclination angle of 78 degrees. This general relativity result is consistent if we assume different noise models, where in here I relax both dispersion measure and spin noise, and the spin noise is even more relaxed. And this is a very relaxed model where we get consistent result from general relativity as well. But saying that we want to see that the Shafir delay that we're measuring is real because we see some discrepancies between the parameters measured individually, we went to the orbital campaigns and measured the Shafir delay using the orbital solution from the global fit and only fitting the Shafir delay at the orbital campaign. And here in red, we show the Shafir delay signal, which is the delay that happens when the gravitational field of the companion delays the arrival of the times. And we see that at conjunction, this delay goes larger. And it's plotted along the orbital campaign at the Parkes, from the Parkes data done at the same time. On the right, I show the orbital campaign at S-band. And we show the fits, and this is the exploration of possible combinations for H3 and STIC, which describes the Shafir delay. And we see that these all result in a consistent measurement. And if you think that this is a bit cryptic, you may be right. So I show this instead. What does this mean in companion mass and inclination angle, right? So we get these results, which are consistent but slightly different for L-band and S-band. And the S-band measurement is also consistent with assuming the general relativity, but there is some variation. And we have to understand why does assuming general relativity give you a result that is slightly different than just measuring Shapiro delay on the orbital campaigns. That being said, this white dwarf can belong amongst the most massive white dwarfs as well. It's just that for now, we have to really pay attention, understand the contribution to the uncertainties and the measurements of the dispersion measure noise and maybe the spin noise. Future steps on this system, we will explore why are these post-Keplerian parameters discrepant with each other if they're measured individually. Can the advance of periastron be affected by this noise? And we will try to investigate what is the real contribution of the earliest Parkes multibeam dataset. And with that, I conclude my observations. I can make some very short comments on where is this moving towards the future. The MeerKAT is planned for expansion with the addition of new antennas. And in the future, a survey of the galactic center is also planned using the S-band receiver at very high frequencies, because the galactic center is it's an area of the galaxy which is very obscured by the interstellar medium. And surveys at the 21 centimeter have so far failed to discover many pulsars in that area. And towards the future, this will become the square kilometer array with huge data rates, and therefore this means that we will have to move to real time computing instead of quasi real time computing that we were doing right now. So yes, that is the problems right now.
Question. I have a few, several, but yeah, go ahead, Nanda.
Thank you very much. Very nice of you. I have two questions. First, it's which are the prospects in your surveys and other MeerKAT surveys for slow pulsars? So which is the slowest you can detect?
The slow. So I can first say the slowest we have detected is just below 4 seconds. Problem is that the search algorithm that we're using is not well tailored. It's not well suited for search looking slow pulsars. We suffer from red noise in the data, and the red noise removal techniques that we use will pretty much kill very low signals. That's why other surveys are being planned of using fast folding algorithm instead, which will be more sensitive to slow pulsars. Other than that, there's also the MeerTrap search, which is not running anymore. But when it was running, it was looking for single pulsars, and that was the one that discovered, for example, the 76 second pulsar in Parkes. So Parkes with MeerKAT, sorry, not with Parkes. So MeerKAT can definitely discover very slow pulsars, just that the surveys that I have been described here don't tailor this population. We tailor binaries and millisecond pulsars.
And also each integration is 10 minutes.
Yes, the integration is 10 minutes. So if we have a very slow pulsar, you might not get the signal to noise either. That is true.
And then especially maybe you mentioned that, but I missed. So now that I mean, there are many neutron binaries of which we can have an idea of the origin. And we have a few neutron star detected gravitational waves in different periods of observing. So how exactly at the moment the two rates compare?
The two rates compare because there has been no new detection of neutron star merger rates, I think, from LIGO. There are two. There's the 2017 one. Yes.
That's the GRE.
That is.
I don't know exactly, but not in 04.
There is one that is in 2019, which is consistent with two neutron stars, but the other ones they could have heavier masses. So it's not clear that they are both neutron stars or intermediate objects between neutron stars and stellar mass black holes, as far as I know. So the detections that people say it's neutron star mergers, I think there's only two that people speak of with certainty. And this is what I'm going back right now. This estimate made from LIGO at the GRTC data release 2.1, they calculated this using the two to confirm neutron star mergers that they have. And the fact that we have been observing for longer and we have not seen any of them should anyway update this value. So this value is probably different right now, but I'm not aware of any studies that has been done in this so far. So this doesn't include O4.
More questions? Maybe one. Do you know? Do you remember off the top of your head the survey completion rates for RelBin and S-band?
RelBin 100%.
Oh, okay.
S1 we haven't reached 10% yet.
Okay.
RelBin is already done. RelBin is done. Scrolls.
And so for the system that you were focusing on, the binary one, so massive white dwarf, maybe you mentioned that. Maybe can you go on one of the slides? Maybe the orbital period companion mass. Maybe.
Okay. This one.
Right. So trying mass function, or maybe the one that showed all the different systems that have been discovered in the type companion type. So
you mean at the surveys? Okay.
The very big one, and then that shows the position of yours. That. Yeah, getting there. Yeah, like these ones. Right.
And go a bit further back and this one.
Right, and so, and for your system, so 1208.
Yes.
You ruled out a white dwarf, a neutron star, because.
No, this is a dull neutron star.
Right. Okay.
This is not a white.
Which one then? Okay, there was another one that was
this one,
the most massive.
Yes,
okay.
The most massive white dwarf, because its orbit, it's extremely circular. Well,
right. Okay.
So when these very massive pulsar white dwarf systems and double neutron star systems have very similar evolution, they're all in this mildly recycled regime in which they don't go to the spin period of just a few milliseconds like in other binaries. The difference is that in the end, the companion has or doesn't have enough mass to go supernova. If it doesn't go supernova, it becomes a white dwarf, the system remains circular. If it goes supernova, there's mass loss, there's a supernova kick, the system becomes eccentric.
Right. Yeah. Sorry, I'm confused.
Sorry. So you think that here you said that it's a white dwarf?
Here,
because,
yes.
And it's not a neutron star because the orbit is very circular.
The companion, the pulsar is a neutron star always.
Yeah. I'm saying that it's double. It's not a double neutron star system.
Yes.
Because the eccentricity is that low.
Yes.
But
So
symmetry.
you recycled. You had accretion somehow because you recycled the neutron star.
Yeah.
But your system is circular.
So the recycling process the first neutron, the pulsar that we see, if it's the old one, is born with eccentricity. There's always a supernova. When the companion evolves and there is mass transfer, this circularizes the orbit. So at the end of recycling, the orbit is circular. So you end up with a recycled pulsar and a helium star, you can say.
So there is no physical process to circularize the orbit after the formation of two neutron stars. So the lack of eccentricity is excluding that.
Yeah. It takes hundreds of million years, even billion years, to circularize the orbit by gravitational wave emission. So the most compact double neutron star systems, they have eccentricities that are around the order of 0.1 or even smaller. This is thought because they are a few 100 million years old and their orbit has been circularized. And still, it's orders of magnitude larger than what we see in pulsar white dwarf binaries.
Yes, Vanessa?
I have data analysis question. I guess so you said that if you want to move towards SKA, you have to be able to really process the data analysis in real time.
Yes.
Considering that you might only have like 5 years, a decade to go, what are the kind of like processes people are working on right now to actually make that happen? Because we've got not that much time left to really do this.
This is
I'll just repeat the question. So basically, considering the huge data rate and the need for real time, what's the approach? What's the idea of doing that in a relatively short time scale?
This is an extremely good question. I don't know the answer of right now.
But do you know, I mean, maybe Emily can ask this, can you actually reuse the tools that are there? Is it possible to use things like tempo and like actually reuse some of the capabilities, or is it never possible?
Tempo, yes. Because timing is very cheap when it comes to data. You only observe the pulsar you want at the place you want for the long time you want, you move your files. What is going to be extremely expensive is the search, where we get all of these many beams that we want to search thoroughly, right? And this is what has to be done in real time. I know there were some discussions among my supervisors that say that maybe searching could be done as data is being recorded and as data is being observed and it's not stored. So you do the Fourier transform while the data is coming onto your telescope, right? And it's going through your backend. But I think we're very far away from this. I know. That's the thing, we will always be looking for the very faint signals, right? If it's not something we have discovered, then it's not going, well, maybe it shows in single pulses, but not if it's periodic like a pulsar. Then you will have to always rely on some way to find periodicity in very signal to noise signals.
Yeah, and I think that right now I don't think there's discussion of moving away from FFT and well, FFA.
No, it isn't.
It's still kind of stays around that area. But then for binaries, like if they're in binaries, those tools on their own, that's not enough. So you need a way to search for the binary. So the Doppler shifting of the period, you need something that would go quickly.
Yes.
In your power spectrum, search a large parameter space. So that's kind of where it's most difficult. Because if you don't search for the binary, for the Doppler shifting of the periods, or changing periods, it's super quick and it would be reasonable to do it in real time. But then searching in binary parameter space, that's where I think the efforts are now being made to find new ways to do that. That
is true. That is the effort right now.
I think we'll try to do that.
And a lot of it is being applied to older data, not only to MeerKAT data, right? So you have the parks surveys, they had observations that were 1 hour long, 72 minutes long. And in there, if you want to find an assuming a constant acceleration is not enough because your observation might be as long as the orbit, right? So therefore, single orbit acceleration is not constant. So you use these templates where you model and search through the Keplerian parameters instead. And this is very expensive as well.
More questions?
Just have a comment on this. That it might be faster to wait for computer companies to faster storage in computers. I mean, if you look at how many people are working on pulsar search techniques in the world and how many are working on actually improving it, that's in the computer, it's clear that
that is true.
Feels wrong though to just it's that. But maybe
that,
yeah. But all right.
I should mention on what you were saying, the galactic center observations, this won't be a survey where we cover a certain area of the sky with short duration observations. We will observe the galactic center for several hours, and this data will be stored, and then we will work on what you were mentioning, like looking for binaries in this very long data, this long time series, instead of focusing on trying to find something in real time. This is data that is going to be stored.
That would also probably be useful for these magnetars. I would expect
yes.
But also magnetars to come out of there.
The thing is that one of the things that we're looking for is the pulsar black hole binary, and if we find one, probably it's a young pulsar, not a recycled pulsar, because the black hole will form before the pulsar actually, so it wouldn't get recycled. So we have to do this binary, and at the same time we have to count that we are looking for slow pulsars in all of this as well. So, but this can be combined. You can use the fast folding algorithm in a search that includes binarity as well.
All right. So thank our speaker again.